particles get a mass, okay, due to the Higgs field, as far as we know. And that is what is shown on the left. And this is what gives you atoms, as shown on the top right. This is what gives you phenomenon like electromagnetism. It is what gives you things like beta decay. So let me take a hypothetical case. Maybe the Higgs field, the expectation value or the average value was 0. Let's think of what would happen to an atom. Electrons would suddenly become massless. They would be like photons. You can't have bound states like atoms. So basically, all matter would just, in some sense, explode. If I were to, hypothetically, if I could turn off the Higgs field to 0, the average value, things would just, in some sense, explode. Okay, because you can't have bound states anymore. So again, rather than our view of the universe like this, okay, it's very hard to simulate what happens when the Higgs field turns on, but I'll try my best. I hope you can appreciate it. So instead of a picture like this is what you will see. Is everybody able to see what is happening?
Yeah.
Okay, so I was just making a joke that the thing is you won't have any of this. You won't have the trees, you won't have the birds, you won't have the stars, you won't have the galaxies. Again, if there was no spontaneous symmetry breaking, you know uh our universe would look something like this: dark and dull, no features, no richness. Maybe there's dark matter here, but anyway, dark matter one can't see, and we do not know what it is. At least we will not be there because there are no atoms. Okay, stars are not there. So let me come back to this pottery, the kintsugi pottery. So what we have hopefully been able to appreciate is that yes, symmetry is very important in our understanding of various facets in sciences, and definitely in understanding many important phenomena in physics, and definitely in fundamental interactions. But very often, you know, it is the unique way in which a symmetry is broken that actually leads to the interesting stuff. It is what leads to the interesting beauty. So I hope I've been able to impart this idea to you that yes, it's kind of like a beautiful synergy between symmetry, but also broken symmetry that actually leads to interesting things in uh, nature. So I thank you for your attention, and I'll be happy to discuss uh, any point.
Excuse me, sir.
Yes.
So you said that when a particle and an antiparticle come together, they annihilate. But there were some particles which were made from one quark and one antiquark. So how did they form? Why didn't the quark and antiquark annihilate?
What I should say is if it's a particle of the same type, if it encounters a particle of if it encounters an antiparticle of the same type, they would annihilate. Okay, but let me also clarify it much further, because what I just said is also not completely correct. See, it does not mean that you cannot have bound states of electron and a positron. In fact, we have created bound states of electron and a positron. So just like you have a hydrogen atom with a proton and an electron, instead of a proton, you can have a positron and an electron. This goes by the name of positronium. Okay, so you can have basically all the theory which you have done for hydrogen atom, you can actually apply in positronium with one minor difference. Remember, you always were putting m electron anywhere. As you might already know, or you might know later, technically what you should put there is what is called the reduced mass. Okay, so it's like m1 m2 divided by m1 plus m2. So the only change you have to make to understand positronium to leading order, you take whatever quantum mechanical theory you have learned about the hydrogen atom. Wherever you see me, you'll replace it by me by 2 essentially. Okay, because positron has the same mass as the electron. So instead of me, you should put the reduced mass, but that is like me square by 2 me, which is me by 2. So apart from a factor of 2, to leading order, everything you have done for the hydrogen atom is also applicable for positronium.
Okay,
Okay,
so it is not annihilation every time.
it's not annihilation every time. See, it's like asking, hey, there's a negative electron, there's a positive proton. Why isn't that electron falling into the proton? Positive way, negative way. This is what bothered the early pioneers of quantum mechanics. And this is how Bohr came up with Bohr quantization and so on. Oh, they were thinking, oh, why doesn't all matter just collapse? Because E minus a proton here, why doesn't it just fall? Okay, so you can have bound states. You can have bound states, but electron and positron, if you impinge on each other or if they meet, they also annihilate. They in fact annihilate to two photons, for example. Okay, if you scatter E plus and E minus, it goes to two photons. Okay, this is what is behind Baba scattering, for example. Okay,
Okay,
in
sir.
some
And
sense.
one more
Yeah.
thing. And one more thing. What is the fundamental reason why symmetries are broken? Like in the particle-antiparticle symmetry, what was the fundamental reason for which it broke?
Yeah. So that is slightly technical in the sense that see all these symmetries which I told you, right? So I was giving an intuitive picture about the way symmetries and like as you might learn in your continuing journey at ICER, when you look at the the mathematical theories which describe these interactions, which goes by the name of quantum field theory, which is the correct framework to understand these interactions. So essentially, it's a combination of quantum mechanics and special relativity. Okay, so in some sense, the quantum mechanics we talk about is actually non-relativistic quantum mechanics. Okay, it's actually a reduction of the truly complete theory to non-relativistic limits. Okay, so if you look at those equations, you will see that if you were to do this charge conjugation transformation for certain interactions, or more specifically the weak nuclear interaction, uh, the form of the equations do not look the same. Okay, the Lagrangian changes. Okay, if you have maybe you some of you have seen Lagrangian for classical mechanics.
Yes.
Similarly, you can write a Lagrangian for these quantum field theories. Okay, you'll see that under these transformations, see the transformations is we talk about rotational symmetry, right? Like we said, the length of the vector, if I rotate it, doesn't change, right? So that is rotational transformation. Similarly, there's charge conjugation transformation, which also has a very clear mathematical definition. There is parity transformation, which again has a very clear. It's analog. It's analogous to things like rotation, right? If you want to go from xy coordinate to x prime y prime, where x prime y prime is rotated, you know the relationship. X prime is x cos theta plus y sine theta, and there is a similar thing for y prime. You can do a similar thing for these transformations as well. And then you will see that certain interactions do not respect CP, charge conjugation and parity combined, or charge conjugation by itself, or parity by itself, and so on. Okay, so I think that is the best way, perhaps, that I can communicate this idea accurately to you.
Okay,
But
sir.
yeah,
Thank you, sir.
other questions or anything, I'll be happy to chat even offline. Uh,
I guess there are a couple of questions in the chat box, Arun.
oh, so since I was in a full screen mode, I would not
Yeah.
have.
There's one I can read out for you, which I find interesting too, which is why is it
Sure, sure.
necessary for there to be more matter than antimatter for our universe to exist? Why can't just an asymmetric distribution of matter and antimatter suffice?
Yeah. So when I say more matter than antimatter, uh, see, if the asymmetry is only little bit, that is kind of dangerous for us, right? So I would say, Kaushik, see, if the asymmetry is only a little bit, okay, it's like Then there might be an antimatter galaxy, which in the earlier epoch of the universe was edging close to our matter galaxy, and dangerous things would happen. So it is good for us that this asymmetry was actually much more significant. Yes, it's an asymmetry. Okay, the claim is not that there was zero antimatter and 100% matter, but the point is that the asymmetry was quite substantial. Okay, because see, it's not like I put one galaxy here, then I put an antimatter galaxy here, and then universe evolves. No, because see, they are also gravitationally coupled, and gravity is symmetric under matter and antimatter. So if the asymmetry was only very small, um, in whatever the 15 billion years the universe is, as far as we know, been in existence, a lot of dangerous things could have happened, and maybe we wouldn't life would not have had enough time to even evolve. Okay, I mean, even under all these great conditions, life is one of the biggest mysteries, right? This is something which we continually are fascinated about, whether there's life out there, SETI, and so on. Yeah, so it's not just the asymmetry, Kaushik, which is important. It is that it is actually quite significant asymmetry. Okay, and I should also say, just to mention, we do not know even now. We roughly know what should happen, but if you were to put me on the spot and say, okay, Arun, tell me. Uh, how this asymmetry actually happen. We measure so many protons, itna antiprotons hai. Can you tell me exactly this equation? Look, I'm able to predict itna matter hoga, itna antimatter hoga. This is also not completely understood. This is again an outstanding problem which we deal with. Okay. Now, IPSA has a question. When Dirac postulated the existence of positrons, did he have an experimental clues leading to the idea? Or did he postulate it simply based on the idea of symmetry? Very good. Okay. Now, I'll refer to an almost original source from which I'm going to answer this. You don't need to read the book, but at least an introductory chapter, which kind of summarizes the history of uh, quantum field theory and particle physics, at least in some sense. It's a book by Weinberg called Quantum Field Theory, Volume 1. Okay, just look at the first chapter. Okay. Now, it's usually claimed that Dirac was only motivated by special relativity. This is partially true. In fact, it was just based on mathematical consistency, theoretical consistency, that he postulated this antiparticle. Okay. Uh, it's not that he did this calculation in his positrons. In fact, he first thought that these particles are protons, because back in the day when he did this, which was around 1927-ish, so on, uh, the only real particles which we knew about were electron, proton, and neutron. Okay, so he thought, this positive particle which my theory ostensibly is predicting might be the proton. But then I think it was probably Wigner or Heisenberg, I could be wrong, immediately showed that it can't be the proton, because the theory also predicted that it should have the same mass. And of course, a proton is around 1 giga electron volt. And as we saw, electron in these funny units physicists like to use is 0.5 mega electron volt. Okay. Now, related to this idea is also a question actually Dirac asked, which might sound a little strange to us today. So he wanted to know why does matter have only electrons in some sense. This sounds like a weird question. It sounds very ambiguous, right? What? But Dirac was actually, so although it's not exactly an experimental question, but he was also thinking about the physical world very closely. He kind of wanted to know, why do you need, in some sense, a spin half particle to form matter? Okay, that's kind of in the modern terminology, that is a way I would frame his thought. Okay, so it was not like, oh, there is this experiment, can I predict it? Although it was not like that, but at the same time, it was not like like that he was just completely immersed in his calculation, and then he saw the symmetry. It was something in tandem. Okay, the mathematical symmetry, in fact, Lorentz invariance, the symmetry of special relativity, dictated that there should be antiparticles. So it's a triumph of theoretical physics. Okay, but he was also thinking of the physical aspects of what is matter, what is happening, just like Einstein. Okay, Einstein didn't one day sit and think, hey, differential geometry is a cool idea, let me do something in differential geometry. He started with very intuitive things, right? Like he started with what will happen if I run as fast as a ray of light, what would I see? He noticed, hopefully not under any unfortunate circumstances, that if a lift is falling, it seems to negate gravity locally. And then somebody pointed out to him that, hey, the tool which you need has already been developed by Lobachevsky and Riemann. It's called non-Euclidean geometry and so on. Okay, so usually there is always some nice synergy between what I would term mathematical intuition and rigor and physical intuition and rigor. Okay, so that's the way I would answer IPSA the question. Vaishak, there is a question
Thank you,
you
sir.
have. Thank you. Yeah. So when you said electrons would explode if the Higgs field would become zero, is that no. Okay, I was just being dramatic because this is a talk. What I said is the atoms would explode. Okay. Yeah. So what I'm saying is, see, atoms have some, electrons around it. Huh? Uh, so if the electrons suddenly become massless, because the electron is a fundamental particle, a proton is not. Proton is composed of bound states. It's a bound state of quark, but the electron is a fundamental particle. And the reason it is 0.5 MeV is because of the Higgs field. So if I could hypothetically turn off the non-zero average value of the Higgs field average value becomes zero, the electron would suddenly become massless. So it's like a massless particle. It's like a photon. You cannot have a bound state like an atom. So the atom would, in some sense, just disintegrate. All the atoms would just disintegrate. So it's in that sense that matter would explode. So it's not that the electrons are exploding. It's that the matter, which is predicated on the fact that there are atoms, and that's a bound state with neutrons, protons, and electrons. That state no longer exists, and it is in that sense that matter would explode, and there would be nothing. Maybe some nuclei will be there, but it won't be what we see.
Thank you, sir.
Did I miss any Mithil? Okay, sorry, probably missed some, and please just hint to me in case I miss anything. Mithil, I don't understand how those baryons can be arranged as an octet. Yes, I've not told you how they can be arranged as a octet, but if you do a course later in your third year, fourth year in nuclear particle physics or quantum field theory, or in group theory, either in the mathematics department or physics, you will very quickly kind of understand what. To tell you in very simple words, um, you uh, so Mithil, just to understand, so have you looked or in quantum mechanics, a world of physics 1 or 2, these simple harmonic oscillator creation and annihilation operators in quantum mechanics? Is that something you guys, all you folks have seen yet, or is that depending on it, I will answer in a way. Maybe Mithil is left. Okay, so let me just say that it is based on a symmetry. Okay, in fact, it is based on what is called SU3 flavor symmetry. Okay, SU3 is just a name for just like orthogonal matrices, you have unitary matrices which satisfy u dagger equal to u dagger u equal to 1. Special just says that its determinant is also 1, and 3 in some sense says that it's a 3 cross 3 matrix. Okay, so you can write a particular symmetry for 3 of these quarks based on what is called SU3 symmetry. And that helps you arrange these particles in what is called a weights and roots diagram. Okay, and that is what gives you that diagram. And I'll just use a word here, which maybe later, years later, you can say, oh, this is what he was talking about. I said there are these off-diagonal elements which have the same charge. There is a horizontal axis, I3. These would correspond to what are called the Catan generators of that group. Okay, things which commute with everything else. So this is where that structure comes from. But I've not told you exactly where it comes from. Just told you that there is some structure. Is there any question I unfortunately missed? The organizers can also please. Is there no charm quark used? I don't know in which context Garvit had asked this. Charm quark is there, but yeah, charm quarks intrinsically are not present in ordinary matter. Yeah, if that was a question. And,
Hello. Hi.
yeah,
I am Arun. I have one question.
sure,
So
sure.
you have discussed about Penrose styling. So
Yeah.
like my question is it any like abstract kind of symmetry, or this can be? I mean, this can be found in crystals, or like do we know any
Yeah.
crystal?
So this I'll have to think of the argument very carefully. So in fact, for ordinary crystals, I think there is a proof which maybe one of the condensed matter people might be able to remember, or one of the chemists will be able to know this much more. I have to think a little bit, but there is almost a proof that the crystalline symmetries cannot have five-fold and seven-fold symmetry or something. Okay, there is a so for a long time it was thought that a crystalline structure based on something like the Penrose tiling. Penrose tiling has a five-fold symmetry, as in if you rotate it by 2 pi by 5 along with reflection symmetry, that is a symmetry of the Penrose tiling. So for a long time, it was thought that you cannot have, but there have been crystalline states like what is sometimes referred to, I believe, as quasi crystals, where this kind of a symmetry appears. I do not know much about this, but the answer is yes, as far as I know, that there are now some observations or experimental evidence for quasi crystals where symmetries corresponding to the Penrose tiling kind of symmetry appears. Yeah.
Like in other ways, my question is like, can we fill a floor with number of like the unit of Penrose styling?
Yeah. So in fact, maybe I should have emphasized. I showed a picture of Penrose, right?
Yes.
He was standing on a floor which had his Penrose tiling on it. So tiling means that it should be able to fill the plane with that. So it's in fact a very intriguing. See, packing problems are actually very interesting, and maybe you can ask Chandrashil or there are actually very interesting things. 2D tiling. How do you pack? Essentially asking if I give you a bunch of oranges or something, what is the most efficient way to pack them in 3 dimensions or D dimensions? There are very beautiful results. So tiling is in that class of problems. Yeah. So you can
Thank you.
tile them.
Thank you.
Okay. If there are no further questions, then shall we call it a day with the permission of the organizers? And thank you for your attention, and thank you for staying slightly longer than I intended. I apologize. My talk took a little longer than what I was planning, but hoping all of you enjoyed. I do not regret it. Hoping that.
Thank you so much, sir, for such a wonderful talk. Indeed, this talk will help us to understand the world in a better way. Thank you so much, sir, once again.
Thank you.